main task of this project is very broad. It asks you to build a project that combines zk technology and machine learning. This is a very broad description. It is very open-ended. So the goal of this short presentation is to give you some ideas of how you can tackle this project. So you might want to start focusing on a sub-branch of zkML. So there's several sub-branches. There's one of the sub-branches is proving correct inference of a machine learning model. This means that you prove that you execute a machine learning model that's maybe signed by a trusted authority, and then you create a proof that this model produces such an outcome on a public input, and you also prove that the model that produced this output is signed, has a correct signature by this trusted authority. This is a very hot application of zkML. It basically allows someone who ran a model to provide a very succinct proof that the model was executed correctly, and also you can prove that your model is signed by some trusted authority. So, for example, maybe the model is signed by the government, and suddenly you have a proof that is succinct, very easy to verify, and this proof says that you pass some criteria, and you're also proving that the model that the government signed this model. So you are providing a proof that the government thinks that you pass this criteria. And yeah, and there's several aspects in here. There's the succinctness, so the proof is very short. It can be very easy to verify as compared to just running the model. You may also want to explore the zk part of zkML for this application. Maybe you want to hide the input as well, or parts of the model. Who knows? Surprise us. There's another sub-branch of zkML which is a bit it is a bit less explored, less developed, because it is significantly more complicated in practice to achieve than correct inference, and it is proving the correct training of a model. So there's some data set, and you want to prove that a model was trained on that data set. That's quite complicated because the training of a model is, as you know, the most expensive part of ML. So training a large language model can cost billions of dollars or millions. Yeah, so proving such a computation with on a snark looks very out of our reach right now, but it is certainly an area that is being researched, and there are certainly teams that are tackling this problem. So you might want to also take a look at this. There's another branch of zkML called federated learning. In federated learning, there are several parties that have data, and they don't want to share their data because it's private. Maybe let's think a network of hospitals. Each hospital has its own data. They don't want to share the data with the other hospitals because they just cannot legally. So, but the hospitals want to train or run some machine learning model on all this data, and they want to merge all the data together, so they have a more deep data set. So federated learning aims to solve this problem because they cannot just share the databases and merge them together because of legal reasons. They would be disclosing patient information to third parties. So federated learning is a branch of machine learning, or zkML, that focuses on allowing this set of parties that have their own private data set to train or run models on this set without revealing the data sets to each other. And yeah, so these are some suggestions. We strongly encourage you to think of your own projects and to surprise us with your creativity. In fact, creativity is one of the judging criteria of this bounty. We want to see. So of course, we want to see projects that deal with zero-knowledge machine learning, but we will value we will have in high regard projects that are very creative, that are built upon an idea that it is surprising and interesting. So yeah, and to finish this short introduction to the bounty, let me give you some suggestions and recommendations. So it might be easy to start by looking at the problem of proving zkML inference, that rather than, for example, proving training, because as I said, proving training is a much harder problem in terms of efficiency than zkML inference, and also there's much less research done there. However, as I said, we value creativity highly. So if you are interested in exploring the training problem, we will also be happy with that, and we will take into account that the training problem is harder than the zkML inference. We also recommend you to try to look and use existing frameworks for zkML or existing domain-specific languages. One way to start a project might be to look for some existing application or project and try to optimize some part of it. For example, one part I believe needs some attention in zkML is how the floating point arithmetic is treated right now. So I think that many projects prove operations with floating point arithmetics in ways that are a bit more expensive than they could be. I think these operations could be improved with some lookup operations, for example, basically lookup operations, maybe last source decomposability, etc. So you might want to go to some existing project in zkML and identify some part of it that's non-optimal and try to come up with a small improvement there. That would be a great way to tackle this bounty. And also, please feel free to approach us and ask us what are these pain points in zkML that you could focus on. We will give you more examples, like the floating point arithmetic example. Yeah. So also, don't be super ambitious. Like always remember that the hackathon lasts what it lasts, a couple of days. This can be a hard problem. Getting into a very big project might sound great, but there might not be time to do that in a couple of days. And yeah, please look at some possible useful links that we added in the description of the bounty. Good luck, and let us know any questions you may have. We will be around.
Hey, I'm Kalzak. I'm from the Gorse team Nethermind, which does security research and audits, and I'm here to talk about the security-driven development bounty for the ETHGlobal event. So just a quick primer on what the point of this bounty is. We're looking to encourage teams at this hackathon to consider security during development. Particularly, we're looking to see use of security tooling and frameworks in addition to the standard test suites that we would typically expect. So what we have prepared is a list of some tools and frameworks to give you some direction and some hints on what you might want to use. You don't have to use all of them. You can just use some or any that you think suit you in particular. And we've just got a list of some sample ones for you. We're going to weigh these differently because some are harder to implement and some are easier, and I'll let you know which ones they are as we go through. So starting with the one we're going to be weighing the highest, this is Forta. And Forta is a real-time monitoring system. So what you can do is you can watch for unexpected behaviors on your protocol. You can set it to monitor whatever you like, really, certain admin actions, withdrawals over a certain time. The way it actually works is it analyzes traces in the call data, and you can write, you can write your bots in TypeScript. Very, very straightforward. You can also consider some important parts of your protocol when monitoring, such as deposits or withdrawal flow assets. That's quite important. Or things like anyone interacting with your protocol using a flash loan. And then once you're monitoring these for these activities, you'll get alerted if this does happen. If you're interested in the Forta bots, we've actually got some links below which you can work through. So that's the first one. Next up, we have fuzzing. Now fuzzing we've actually split into two categories because one is a lot easier to do and one is a bit harder. So you've got stateless and stateful fuzzing. But before we jump into that, I'll give you a quick primer on what they are. So fuzzing involves automatically generating a wide range of inputs to test a smart contract's behavior. You can set expectations, such as the function shouldn't revert or it should return a particular type of value or something like that. And if these expectations are broken, after giving these random inputs, the fuzzer will tell you what the input was. So now you know what's causing a problem in your code and then you can fix it. So that's a general breakdown on what fuzzing is. So now we can jump into the particular versions. So we'll start with stateless. Stateless fuzzing is fantastic for individual functions, right? So making sure that math or calculation-heavy functions work correctly. So you focus on a particular function, and it'll test random inputs to make sure it works correctly. Now this one, we've got it weighed reasonably well, but it is easier than stateful fuzzing. So we're taking that in mind. And you can actually add stateless fuzzing into Foundry very easily because it's natively supported. So we've got a little link down there, how you can add fuzzing into your standard test suite with very, very little effort. Next up, we have stateful fuzzing. This one is much more advanced than stateless. And the way it works is, instead of trying random inputs on one function, stateful fuzzing focuses on the contract as a whole. So it helps to test the contract behavior through various state transitions and sequences of transactions. So, as in the name, stateful fuzzing, the contract state, so storage and stuff is taken into account. The same general concept or idea exists though. You set your invariants and the fuzz is going to try a series of transactions, interactions from different addresses, different call data, different functions, in order to find a way to break your invariants you've set. So an example of an invariant in this case could be a lending protocol where no more than 50% of the assets can be loaned out at any given time. And if this invariant is broken, the stateful fuzzer will tell you what sequence of calls is needed, and then you can figure out a way to fix it as well. So for here, we've got a list to Echidna, which is a fantastic tool for stateful fuzzing. The final one we've got listed as a suggestion here is symbolic execution. So symbolic execution is similar, quote unquote, to fuzzing, but there's some important differences to note. So unlike fuzzing, input values are not concrete. So with fuzzing, it'll choose random values and then it'll run them through. But instead, for symbolic execution, it'll explore paths in the code. And then you'll have a constraint solver that will see if there's any feasible inputs that will satisfy the path conditions to what you want. So let's say an example is we've got a function add, which adds 2 numbers, and we set a constraint, it should not be possible to return 10. What will happen is symbolic execution will turn that function into a series of paths, and then it will find some given input in a more mathematical sense. Instead of randomly guessing values, it'll find these inputs, 2 inputs that will result in the path we don't want, which is 10. So for example, that could be 5 and 5. The benefit of symbolic execution over standard fuzzing is you're not relying on random values. Instead, you're exploring all possible paths, ensuring really comprehensive coverage. Keep in mind though, it is pretty computationally demanding for like multiple functions that have got a lot going on. So typically you want to apply this to specific functions with core logic, quite math heavy things that you want to make sure they behave correctly. We've listed here a resource to Halmos, which can actually connect into Foundry in quite a simple way. So it gives you easy access to symbolic execution and you don't have to worry about the headaches of doing much of the behind the scenes stuff yourself. So these examples should be a pretty good primer, and it should give you a good idea what you want to get started on. One thing I want to note is we're looking for quality of coverage as well. So just adding these tools and putting them on, an ERC20 decimals thing, which never changes, obviously that's a relatively unimportant area. So if you manage to apply some of these security tools in the more important critical aspects of your code, then that's what obviously you're going to weigh and consider that a lot stronger. And other thing we want to note is if you have any other ideas on security tools which we haven't mentioned here, you can feel free to use them as well. This list wasn't meant to be comprehensive by any means. So good luck and have fun.
Hello, I'm Swapno. I'm the head of innovation at Nethermind, and I also work on the Switchboard team in Nethermind. Switchboard team is focused on pre-confirmations research and development, and we're currently implementing some proof of concepts for some new types of pre-confirmations on Ethereum and for base rollups. So pre-confirmations stand to bring sub-second sequencing to Ethereum and base rollups. Pre-confirmations work by users communicating their transactions to the future proposers directly or through a gateway, where the future proposer would sign on their user's transactions ahead of time, confirming that they would include the transaction when the block comes about. Pre-confirmations can bring the best of experiences to base rollups, because currently base rollups only produce blocks in every L1 block, which is every 12 seconds. Pre-confirmations would let base rollups produce blocks between those 12 seconds and give users very fast confirmations. There's quite a few R&D questions open in the pre-confirmations world. One of the big ones is pricing of pre-confirmations. How should the user and validator come to agree on the pricing of pre-confirmations? Mechanisms like EIP 1559 would bring the most transparency and most ease of use to pre-confirmations. There's a lot of infrastructure to be built for execution reconfirmations. Execution reconfirmations are where the user says, hey, I want to execute this transaction and get these results as a result of executing these transactions. Think of things like intents as being similar. And there needs to be built some infrastructure to enable these reconfirmations. We also need some data dashboards to bring some transparency into the world of reconfirmations. The current reconfirmation pipeline can be quite complex if you include gateways and whatnot. And data dashboards to bring some transparency here are much needed. I'll be at the Nethermind booth at ETH Brussels. So if you have any more questions or ideas about reconfirmations, come talk to me.
Hey, my name is Jörg, and I am the co-CTO at Nethermind. My CTO-ship covers all of the StarkNet-related activities in the company, which involves writing full nodes, consensus algorithms, zero-knowledge proof systems, block explorers, APIs, SDKs, and so on, the whole stack. The entire L2 narrative was around scaling Ethereum, and this is the reason that we got involved. And from there, most people have been focusing on cheaper fees. Let's do the same thing, but just keep the fees as low as possible, and people can then not pay $10 for doing one swap, right? While this is incredibly useful work, this is not why we build bigger computers. It never has been. We didn't build Doom to show that you can't play games. We built Doom to show what the next game could look like. Everything is about what can you do with more and more compute. Take other examples, like AI is a simple algorithm from the 1970s, 1980s, with a lot of complexities to make it work, but it only works because of things like Blackwell, the absolutely gigantic machines. So it's not exciting to deploy Aave or Uniswap on StarkNet or on Base and have cheaper fees. This is cool, but it's not like the mind-blowing thing. What's interesting is, can we use larger programs in higher complexity classes for problems that haven't been solved yet, right? The traditional finance systems use much more complicated simulation and routing algorithms than crypto does. So to understand what this problem is about, if you're a computer scientist, think of all of the high complexity classes. Think about NP problems. Think about large scale compute challenges that you could possibly leverage to solve problems. And think would it be different if this thing was hosted on a blockchain? Would it be different if it was triggered automatically every time you took an action? So that's one way of thinking about it. If you're not familiar with that, then go read up on high complexity class problems for the first couple hours of the hackathon and try to see where they fit. I'll give you some examples. If you're trying to do some sort of map-based thing, then you have the traveling salesman's problem as a way of doing efficient routing. That is NP. I've forgotten exactly which NP subclass it is, but you can't really solve that for large numbers. But there are definitely lots of heuristic algorithms that are still very, very high, in the orders of n cubed and squared and so on. So these kind of issues, that's maps. Think about order routing, which is flow-based problems. How do I pump as much liquidity through different channels in order to get the maximum value at the end? This is not done on chain and could totally be done. So an example of something that you could hack on is, what if I did a trade on StarkNet, through Avenue or some other aggregate protocol? At the end, I actually try to burn a bunch of gas to compute any post-trade arbitrage opportunities, so no one can backrun you. Your algorithm backruns yourself. You never lose the value there. It's not actually possible because that would require a lot more compute, but it's already tangible, so you can already start doing it more efficiently because of this. Or say you're a protocol and you need to do some housekeeping. You can do this by aggregating across all the users. So instead of your user just doing a swap or setting a position in LP or doing some basic action, they do this and they do the housekeeping for everyone else, and they don't care because it costs a cent, right? So this is where this becomes interesting, is now that the protocols can do the housekeeping by leveraging the protocol users. So that's a whole set of problems that you could look at. Let's see, are there more things that you could do with this? Absolutely, and this is kind of where I want you to be the creatives and figure out, what can you do now that you've got more compute and more storage than you ever did before? You can also think how does this look like in future rollouts? You've got L2s, they've got, well, the L1s are bounded basically by the amount of storage they can put into memory. How much data can you access quickly and cheaply, right? So they try to keep it within this memory constraint and then distribute it over thousands of validators. The L2s are not going to have this problem. They're going to be max 100 machines distributed, or maybe 50, or maybe 1,000. But we'll be able to say all of these are top of the line, sort of like enterprise grade machines, right, with 160 terabytes of RAM, right? That exists. Like, I'm not even sure that that's the upper bound. I'm pretty sure it's much higher. So if you have all these machines, then storage is actually pretty cheap. So make a completely on-chain application where like all of the data is stored there. But that's feasible now in L2s. Yeah. Anyway, you get the idea. Don't do the same thing. Do something more, with what we have. That's where the interesting things are. Yeah. If you're interested in more ideas along this space, you can DM me on Discord or ask any of the people from Nethermind. To be honest, it's really hard to look at the state of play that currently is and imagine what the future is, but that's the whole fun of a hackathon. So do something absolutely nuts and see what you come up with.